We are starting a new module, Module 2, which deals mostly about stoichiometry. And stoichiometry is the section of chemistry that deals with proportions in reactions, moles and grams, in reactants and products, and we will talk about leftovers or and yield and limiting reagent and etc etc. But before we jump into reactions and balancing reactions and all that fun stuff that awaits us ahead, it's important to talk a little bit more about atomic mass and molecular mass so that we really understand the what's behind these numbers that we see in the periodic table. First of all, I want to distinguish between two terms, isotopic mass and atomic mass. In the last module, we were talking about that the definition of the Avogadro's number is the number of atoms existing in carbon-12, that is exactly 12 grams. However, when you go to the periodic table, this is not exactly 12 grams. This is 12,011. This number, the 12,011, is the weighted average that corresponds to the presence of different kinds of isotopes present in our planet, or actually it should be in the biosphere, right, where we do most of all our experiments. While this proportion is not constant, so depending on the country and depending on the atmosphere or in the sea, it mostly holds true. So the atomic mass is what you see in the periodic table. And that's, as I said, the weighted average of the isotope mass. This is the isotopic mass of each of the isotopes. As you can see, carbon-12, carbon-13, carbon-14 have different masses, different atomic masses, even though the right term would be different isotopic masses. Notice that what makes a carbon is the number of protons. Carbon-12 has 6 protons and 6 neutrons. Let me just make sure this is a review, hopefully. Carbon-13 has 6 protons and 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. Okay, so it's a carbon because it has 6 protons. But the number of neutrons change. So overall, the carbon-14 is a much heavier, or not much heavier, but definitely heavier atom. So how do we get this number? So this number, as I said, is the weighted average. So carbon-12 is present in 98.99%, so 98.99%, plus carbon-13 is this times 1%, and 14, it's very tiny. I'm sure you use carbon-14 in NMR, in organic chemistry, and that's a much smaller 0.01%. So if you plug this into the calculator, you get the atomic mass. Does that make sense? So again, the atomic mass is it can only be used for moles, for macroscopic events. If you identify a single molecule or single atom, that's either carbon-12, carbon-13, or 14. It cannot be a mix of both, or the three. Okay. Therefore, molecules will also, when we talk about, say, molecule of methane, we will assume that if we have 1 mole of methane, the proportion of carbons in here will hold true as for the isotopes 12, 13, and 14. All right. So when we have a microscopic amount of methane, we will use the atomic mass to calculate its molecular mass. So for the molecular mass, we will use 12.011 plus 4 times, it's mostly 1.0, okay, and this will give you, which is around 16.11 grams per mole. This is the molecular mass, which uses, this is what we call molar mass. It's molar mass if we use the atomic mass. If we talk about just one single molecule of methane, say carbon-12, instead of 12.011, we'll have to use exactly 12.0 plus 4, depending on the isotope of hydrogen, but then that would be exactly 16.1.0. Does that make sense? All right, so I just wanted to make sure that we understand that distinction. All right, let's talk about the different, even though somewhat related, property, which is the percent mass of elements in compounds. Let me give you an example. As we said, methane. The percent mass of element was an important property when chemists in the 19th century had no clue of the relationship between elements in a specific compound or in a formula. So the only way they could figure out the proportions is by counting the percent of mass of the element in a compound. So for example, what is the percent mass of, say, the element carbon in methane? So say that if you have 1 mole of methane, to calculate the percent of mass of carbon, you have 12.11 or 11 grams over the overall mass of the molecule, which is 16.11, as we calculated before. This 16 again comes from the mass times 4 times 1, which is the atomic mass of hydrogen. All right, so this number is called the percent mass, in this case, of carbon in the molecule of methane. Let's do an exercise. So here you have a question, and it's asking which of the following compounds contain the largest mass percent of hydrogen. Notice that it's trying to confuse you here, because this property, the percent mass of the element into a compound, is intrinsic to the molecule, so it does not matter the mass. These 10 grams could be 100, could be 20, this we are not going to use this. All right, so in this case, however, we need to calculate for hydrogen. So in methane, the percent of mass will be 4 over, roughly 4 over 16, right? If there were 12 over 16 was carbon, 4 over 16 is the other, the hydrogen. For this case, ethane, what is the mass of hydrogen in 1 mole? We can use 1 mole, but it doesn't matter, because in the end it's just a proportion. What is the percent mass of hydrogen in ethane? We have 6, yeah, in 1 mole there will be 6 grams of hydrogen overall. And how many grams there will be of 1 mole? So for ethane you have 12, and I'm doing approximate numbers here. 12 times 2 plus 6, this is 24, this is 30 grams. Okay, so in 1 mole there will be 30 grams of the molecule. All right, and in water, in 1 mole of water there will be 2 grams of hydrogen over how many? Again, this would be multiplied by 100, of course, but we're just interested in comparing numbers, so whatever it is that we obtain, we can multiply by 100 or not. So the percent mass of hydrogen in water is, what is the molecular mass of water? For water, the molecular mass is 2 plus 16 is 18 grams per mole. So 18 grams in the molecule. Okay, and in sulfur, again, what is the molecular mass of sulfur? It'll be 2. You go to a periodic table. Actually, we had one here. I think we had sulfur here. It's around 32. So it's 32. This means it's 34. The percent mass, I keep forgetting the 100, it'll be 2 grams of hydrogen for each 34 grams of molecule. I chose 1 mole just so that we can use directly the molecular mass. Whichever is the largest number here, this is 1/4. Let me see, this is less than 1/4. This is definitely less than 1/4, and this is definitely less than 1/4. Methane is the compound with the highest, largest mass percent of hydrogen. Hopefully that makes some sense.